All right, so let's talk about Ohm's law, voltage, current, resistance. First, an analogy. So we're going to relate this to water instead. So if we look at this pipe, there's no difference from end to end. Is the water going to move? No, of course it's not going to move. There's no difference in energy. What about this one? Now we have a high potential energy over here. We have a lower potential energy over here, gravitational potential. Yeah, that water is going to move. There's a difference in energy. There's a reason for it to flow from one end, high potential, to the other end, low potential. It's going to run downhill, basically. So another example, we have a huge tank of water and a small tank of water. So this is under higher pressure, this is under lower pressure. Where's it going to go? It's going to flow from one to the next. And when is it going to stop? Well, it's not going to keep going. Once this tank kind of comes out to the same level, and they're same. Now there's no difference in pressure, so there's no reason for it to flow anymore. It's going to stop when it reaches equilibrium. So what if I wanted to move that water back into the bigger tank? Well, I'm going to have to do work to do that. So I'm going to have to use a pump to actually put pressure into the system to say, take this water, push it uphill and back into the big tank. I got to put in energy, do work to make that happen. Okay? All right, so far so good. We have water flowing only when there's a difference in potential energy specifically. So electrically, this is going to go from high pressure to low pressure, and I'm going to ignore the formatting error. I'm going to let that go. That makes me twitch, but that's okay. So our downhill here is from the higher potential on one side of the battery to the lower potential on the other side of the battery. As long as we have a difference in potential energy there, and difference in potential energy per charge, thanks to chemistry, hooray, we're going to get electrons to flow as long as they have a path, just like the water did when we added a pump. So the battery is the pump. Okay, when we actually get things flowing, which of these rivers has a stronger current? If you said it was this guy, yep, you are correct. Why? Again, if we have a large potential energy and a small potential energy and a path to go down, you'll get a current. You'll get water moving down that path. So the current refers to the flow of charge instead of water. So it's flow of charges actually leaving the negative side of the battery, going toward the positive side of the battery, which is actually the opposite of how we usually define current. Typically, we're defining current in the positive direction, but again, that convention was established long before we knew it was the electrons that were moving. So it doesn't really matter for what we're doing. The important part is the current we're looking at is the amount of charge going by per time. Charge in capital Q for quantity of charge, T for time. Current, it's measured in amperes because somebody studied it in an ampere. And we use a capital I for the variable because there's a Latin root called impere, which means to go, to flow. So that's kind of where that comes from. So capital I for current. Ohm's law is going to connect these ideas, the idea of current, flowing charge, potential difference between two different places, and the resistance that something is going to experience. Different things are going to have different amounts of resistance to that flow of charge. So if we put 1 volt of potential difference and we have 1 amp going through it, then that we define that to be there's 1 ohm of resistance. So it's measured in ohms. If we have think back to our water example, right? If we have big wide pipes, there's less resistance. It's easier for water to flow. If we have thin, skinny pipes, it's harder to push water through there. When you're leaving the cafeteria, if there's only one door open and everyone has to funnel out the one door, there's more resistance. If people open many doors, you have a wider exit, there's less resistance and more flow because of that. Typically in circuits as we deal with them, the wires themselves do have a tiny bit of resistance, but really not much. So it's really over those short distances, they're fairly negligible. They're very, very low. The resistors, though, light bulbs, toasters, things you put in the way, these are designed to have a very high resistance because they want to turn the potential energy of the electrons into something more useful, light, heat, etc. So we have high resistance here, very, very tiny resistance in the wires, enough that we can neglect it, unless we go for a very, very long distance, and that starts to build up. Transmission lines, now you're talking like 2 to 6% of energy lost along the way. Okay, the big important point, Ohm's law, the idea that voltage